I'm ready. It's being recorded. Continue. By the way, if you want to ask the questions during the talk, please, you're very welcome, and actually it helps. So stop me, but do it in such a way that I will hear you. Okay, so all right, so it's actually about embedding theorems on bi-disk and multi-disks. But all my talk, we will work basically without any holomorphic functions. It turns out that the question about the embedding for holomorphic functions, in many cases, but not in all cases, is equivalent to the 100% equivalent to the question just about some embedding on graphs. And so the talk mostly will be about embedding on graphs, but application is to holomorphic function of several complex variables. Okay, so of course there is a one variable situation, but it's well known. I will call it trivial, even though it's not, I mean, completely trivial, but I will just use the word trivial. So embedding theorems in the Russian tradition, it's certain type of theorems you will see soon, but in like Western tradition, it's called paraproducts. So this is the same as to research certain boundedness properties of operators, which are called paraproducts. And in our case, because we have several variables and they're independent, these are so-called multi-parameter paraproducts. In the talk, it will be b-parameter paraproducts. And so there are many applications in PDE to linear and nonlinear equations. But this I will not touch at all. I will basically go to the purely very simple sort of Olympiad problem about positive numbers. So first we will consider a toy problem, which is extremely simple. So here it is. Suppose we have interval 0, 1, and then dyadic intervals, subintervals of 0, 1. So 0, 1 itself, its left half, right half, 4 grandchildren, etc. And for every dyadic interval, we are given a non-negative number. So there is an assignment for each I, we have alpha I. And these alpha I's, they have a certain property. It's property 1. So if you sum up all possible alpha I's such that I lies inside J, then the sum of these guys is less or equal than the Lebesgue measure of J. So it's a property of this assignment of positive numbers. And now we want to ask, is there another assignment? And this other assignment is not the assignment of positive numbers, but it's assignment to each interval of a certain subset of this interval. Such that all subsets for all dyadic intervals of any kind of generation are all pairwise disjoint. Each EI lies inside I, and measure of EI is given by the same number alpha I, which I pronounced before. Now, such assignment is possible. I mean, it's necessary that such an assignment exists. It's necessary to have condition 1. It's triviality because of the disjointness. Now, the question, is it also sufficient? Well, the answer is yes, it is necessary and sufficient. And this assignment is actually very simple. Maybe I have a picture. No, I don't have a picture, which is a little bit strange. I thought I have a picture, but if I would have a picture, you would see that it can be done in 30 seconds. You really, given this alpha I's with property 1, you can find disjoint measurable sets inside each I, such that measure of AI is alpha I, they're all disjoint, and so we're done. The problem is solved. So this assignment, yeah, by the way, this is the picture. So you choose some measurable set, and first of all, you always think that alpha i's are 0 after a certain place. So there are only finitely many, but many of them. And you start for very small intervals, you assign small guys of this color to very small intervals. And it's trivial because the intervals are disjoint. But the next generation are already not disjoint. You consider their fathers, and you need to assign another set. But because of the condition 1, you will have a place to assign next time again. And when you go to grandfathers, again, you use condition 1, you still have place to assign. So it's a triviality. And there are many ways to make this assignment. And it doesn't matter that these are intervals. For example, if you would have cubes, and again, dyadic cubes, and the same condition 1, but now i's are not intervals, not dyadic intervals, but dyadic cubes, with the same condition where this will be Lebesgue measure of the ambient cube, same algorithm. It's triviality. So that's the picture of this. So you first assign to a very small one, then you have place to assign to the fathers, then you have place to assign to grandfather. So it's nothing. Okay, and now let us make our life harder. Suppose now we're given so we have first assignment and second assignment. So first assignment of numbers. But now we assign numbers not to dyadic intervals, but to dyadic rectangles, not to squares, like on the previous picture, but to dyadic rectangles. So each dyadic rectangle has a number attached to it. It's a non-negative number. And now we need to have another assignment. We need to choose in each dyadic rectangle a subset, measurable subset, such that all these subsets for all dyadic rectangles would be disjoint, and such that the measure of these sets would be given numbers alphas. So what is the necessary condition? So what is the analog of condition 1 in this situation? The analog of condition 1 is the following. So you should take any number of dyadic rectangles. Well, let's think finite number. So this S here, this script S, is a finite collection of dyadic rectangles. You take the union of all of them and measure it. Then you take all alphas in this set and sum them up. And this condition is obviously absolutely necessary for having this assignment. And the question is it sufficient? That's the first question. And the second question, why I'm choosing now the whole bunch of rectangles? Why I have to choose a certain family S? Why not to choose, as it was before, just one rectangle and consider the same type of condition? Well, the answer to the second question is that if you have condition 2 light, meaning that you choose here not any subfamily, but just very simple subfamilies consisting of one dyadic rectangle. So this special condition, let's call it 2 light, will not be sufficient. And this is a very difficult example constructed by Leonard Carlson, never published, and you can find it in one work of Terry Tao. So on the other hand, if you consider the whole condition too, which is obviously necessary for assignment of disjoint sets, it turns out that it's also sufficient. And now you cannot do it like I did it 30 seconds ago by just simple picture. It's a difficult theorem. So it's a difficult theorem, some combinatorial measure theorem, and however, it's correct. Well, there are several proofs. There is a proof of Tino-Haninen, and there is, so these proofs are not geometric actually. And there is one geometric proof of Jill Pfeiffer and Alex Barron, quite not easy. Well, let me cite this Tino-Haninen theorem. It even doesn't depend on whether these are dyadic rectangles. It can be just any Borel sets. So we have a countable collection of Borel sets, and we have the family of positive numbers, non-negative numbers assigned to these Borel sets. And they have this condition. It's the analog of condition 2 above. So you sum all positive numbers for all elements of your collection such that this element lies inside omega, and omega I will explain in a second, and this should be less than measure of omega. And what is omega? And omega is any union of subcollection of S. So such combinatorial stuff. And then you can make the assignment not of numbers, but of disjoint sets to each Borel set S, such that they will be inside each element, they will be disjoint, and their measure will be alpha S. So this is theorem of Haninen. As I said, it's not an easy result. But now let me tell you why I need it. So this geometric results is just piece of puzzle which I want to present. So this is so-called weighted embeddings. So here is the main thing in one-dimensional case. So in one-dimensional case, as I said, it's all very well known and very easy. So it doesn't look very geometric. So this is the question we would like to research. And as I said, in one-dimensional case, it's researched like 40, 60, 80 years ago. So given measure on 0, 1, and any function in L2 with respect to this measure, you take all possible dyadic subintervals, integrate this function with respect to this measure, square, multiply by a certain given sequence, and sum up. And left-hand side should be less than the right-hand side. It's called embedding theorem. Why it's called embedding theorem? Because we start with L2 mu, and we, by this operation, we make a certain operator which embeds L2 mu to a certain discrete space L2 with the weight Wi. So this is why it's called embedding. And it's very well known what is the answer. And the answer actually can be read from here basically immediately. You just test 5 on very simple functions. So take, instead of general f, take characteristic function of any dyadic interval. So when you take characteristic function of any dyadic interval, and you sum up over all dyadic intervals, many guys here will be 0. Because if dyadic interval doesn't intersect this dyadic interval, it becomes 0. So when you just plug f equals characteristic function of dyadic interval j, you will have this condition. So for every dyadic j, certain sum is less than constant measure of j. And this condition is obviously necessary because we just tested it on characteristic function. And the theorem of Carlson-Sawyer is that it is also sufficient. And how it's proved, let me prove it in 30 seconds. So first step is our assignment. We take these numbers, you see this is the number, wi times mu I squared, and divide by this c. This is our alpha I. By the theorem which I cited above, one-dimensional, we will have a disjoint set assignment with corresponding measures of these disjoint sets. After that, there is step number 2. So here I said, let's take alpha I like that and use the previous assignment theorem. But on the next step, we will need something else. So that's this geometric part is only like, how to say, 50% of the proof. And another 50% of the proof is the second step. After you make this assignment, there is a very simple reason which shows that to prove the embedding, you need just to use the following fact, that dyadic maximal function with respect to any measure is bounded. And this is just a theorem, you can say a theorem from probability, because it's Dup's theorem. It said that any martingale maximal function is bounded in any LP if P is between 1 and infinity. And that's a classical thing, of course, and we just use it. And step 1 assignment, step 2 Dup's theorem gives that we have 5. So in one-dimensional case, as I said, I will call it triviality. Well, it's not absolute triviality. Dup's theorem is a big thing, and assignment is also, even though it's very easy, but still one need to invent that you should do assignment. So it's not completely trivial, but model of what I will do next, it's very trivial. Okay, so we make it harder. So the same idea as before. Instead of considering dyadic squares, we are now in dimension 2, but we are not considering dyadic squares. We can consider dyadic rectangles. On the right-hand side, we have exactly what we had before, L2 mu. So it's a square of the norm of F in space L2 mu. But on the left-hand side, we have absolutely huge sum. Why it's absolutely huge? Because these are all dyadic rectangles. It's not dyadic squares. You know, dyadic squares, there are many of them, but imagine how much more there are dyadic rectangles. The squares have the same horizontal and vertical size, and dyadic rectangles, they can be absolutely different from that. They can be very long, they will be very tall, whatever you want. There are many, many, many dyadic rectangles, much more than dyadic squares. So this sum is absolutely incredibly huge. And you want it to be bounded by the same right-hand side. As I said, if you solve 7, which has nothing to do with analytic function on the face of this page, it's actually equivalent to some embedding theorem for analytic function in B-disk. Equivalent. It's not trivial. It's soft analysis, but beautiful, rather long, and not trivial. But believe me, so as soon as we solve this problem, and by the way, this problem, you can think that f is positive function. So mu is positive measure. So it's a problem about positive numbers. Moreover, as always, you can think that these w's are zeros after a certain place. So it's a problem about finitely many positive numbers. And you need to give necessary and sufficient condition for these boundaries. And of course, we want to go the same way as before. Let's take a very simple test function. let's take function f, which is characteristic function of some fixed dyadic I0 cross J0 or I1 cross J1, some fixed dyadic rectangle. And plug it in here because it's one. Here there will be measure of this dyadic rectangle. Here it's more or less clear what will happen. And we will have a necessary condition. And this necessary condition is not sufficient. And it was proved by, as I said already, Carlson, and then, as I said, you can read it in some paper of Tao, even for measure mu, which is Lebesgue measure. So the trivial necessary condition which worked in dimension 1 doesn't work in dimension 2. But then Alice Chang, for the case when mu is Lebesgue measure, invented condition which is sufficient and also necessary. And this condition is the following. So instead of taking the characteristic function of one dyadic rectangle and plug it into 7 above, let's take function f, which is characteristic function of the union of dyadic rectangles. Now, union of dyadic rectangles can be a very complicated set, right? You can imagine it's like this, like this, like this, like this, like this. So we just consider such sets, finite union of dyadic rectangles, give them specific name omega and call them dyadic open sets. They are not open sets, so if you wish, they are open sets because you can consider only open rectangles. But here is the Chang condition, but remember it was only for measure mu, which is Lebesgue measure. So if you have condition 8 for Lebesgue measure mu, it is equivalent to this embedding 7. Again, for Lebesgue measure mu. Okay, what about not Lebesgue measure mu? Because for us, our problem appeared from what Nicolas Arcozzi did for Dirichlet spaces. And for Dirichlet spaces, you need not Lebesgue measure mu. You need just any measure mu. You should describe all such measures. So it has nothing to do with Lebesgue measure. And then this condition being always necessary will stop to be sufficient. There are many examples of that. They are non-trivial, but so it again stops to be sufficient. But there is a certain silver lining, because the problem appears from holomorphic functions, in particular from Dirichlet spaces. You can recompute what these weights will be if you want to apply it to, say, spaces of functions in Dirichlet class. If you want to apply it to analytic functions in B-disk, but for Dirichlet space. And after some not very difficult computation, you can see that this problem becomes the problem where this Wi cross J is just identically 1. So there is no Wi cross J, just 1. Now, let me tell you something. First of all, Dirichlet space is not, I mean, it's an interesting space, but there is a whole scale of spaces, right? Because there is a Dirichlet, there is Hardy. Hardy has 0 smoothness, Dirichlet has 1/2 smoothness. And in between, there is a whole scale of analytic functions of 2 variables with smoothnesses between 0 and 1/2. And by the way, smoothness can be something in one variable, something else in another variable. So there is a whole scale of spaces. And for each scale of spaces, you can recompute this W. And as I said, for Dirichlet, it will be 1. And for, say, weighted Dirichlet, with another smoothness, you can always compute what it is. I will not tell you, I don't have time, but it will always have a tensor form. It will be a certain function of I multiplied by a certain function of j. So this weight will be a tensor product of two weights, each like in one variable. Here variable is dyadic thing, so but still. Okay, so the simplest and maybe one of the most interesting cases is when this tensor product degenerates to just identically 1. But if it doesn't degenerate to identically 1, it's length of I to a certain power, length of j to some other power. It's still a tensor product, and it's still an interesting question which corresponds to holomorphic functions of a certain smoothness. And let me tell you, corresponds precisely. So if and only if. Okay, so what we know at this moment? We know that for Lebesgue measure, Alice Chang gave the answer, and this answer is this necessary and sufficient condition, and I will call it from now on Carlesson-Chang condition. So this type of condition will be called Carlesson-Chang, but remember, she did it only for mu equals Lebesgue measure. We're not interested in Lebesgue measure, we're interested in general measure, but for us, this will be the product. So this will be a tensor product of Wi and some other W tilde j. Because our problem appeared from the problem in BDISC about analytic functions of certain class. So here I list what we know, what we don't know about that, and so I cite here this Carlesson example, which you can find in Tau, some kind of another inequality, number 10, which is also pertinent here. But let me, probably I should come to the main theorem. So let's do it here. Let's read. So we have arbitrary mu, and let's start with W equal identically 1. And I was working on the square. So it's two-dimensional case. I here say T2. And for this case, we can give necessary and sufficient condition for this embedding. So full description of mu's follows, and if you remember, this should correspond, T2 should correspond to BDISC, T3 should correspond to disk times disk times disk, so 3 disk. We hope that the same is true for any dimension, but we cannot go beyond dimension 3. So for dimension 4, we already don't know what happens. Our answer for the case, as I said, W equals 1, which corresponds to Dirichlet space for this dimension 2 and dimension 3 is very counterintuitive. It consists of 2 parts. So embedding is equivalent to Carlesson-Chang, but remember now W is 1. There is nothing counterintuitive here. It's what any reasonable person would suggest. that you should take Carlson-Chang, put your weight W equals 1, and this should be the right condition. And that turned out to be true. That's true result. But what is counterintuitive is that this condition turns out also equivalent to this condition, where instead of dyadic open set, you just take dyadic box. So this is why it's called box condition. You immediately should say, it contradicts, you just said that Carlson proved that box condition is not the same as Carlson-Chang condition. Yes, but he used that he can use W. We don't have W. So he had the freedom because there was a W here in front. And then for very many W's, these two conditions are very different. And he gave this quite interesting geometric example. But in our case, W is identically 1. So you have freedom only to work with mu. And it turns out that by working just with mu, you cannot distinguish between Carlson-Chang and box condition. They're equivalent. And a strange thing is that, of course, we didn't believe in this. We proved that Carlson-Chang is equivalent to embedding. And for like 8 months or maybe a year, we were trying to construct a counterexample that box condition is not equivalent. And of course, we didn't construct this counterexample because it turned out that they're equivalent. But the proof is completely independent from the previous proof. So these are kind of two different proofs. So 1 is equivalent to 2 is equivalent to 3, and so 2 is equivalent to 3, but there is no clean geometric proof. Now, I want to call your attention that what is proved here is some theorem from, I don't know, combinatorial geometry, which sounds very strange. So given any positive measure on the plane, if you have this condition, 11, that if you take all dyadic rectangles inside given dyadic rectangle square, sum, and it turns out to be bounded by constant times measure of the ambient dyadic rectangle. So if you have this condition for measure, then you automatically have this condition for measure. So just cross of W, it's 1. Then for each dyadic open set, and dyadic open set is basically any open set. So then instead of box, you can consider any open set. And now take these guys, these rectangles inside the open set. Square them, sum, and it will be then another constant times the measure of this open set. So it's true for all measures. Now, why it's difficult? Because if you are given an open set, it's very easy to break it, or almost break it, to disjoint dyadic squares. But it's impossible to break it to disjoint dyadic rectangles. Well, if you do it, of course, you can do it because squares are rectangles, but then you lose a huge amount of r's in the left-hand side. So you will prove something like that, but left-hand side will be much, much smaller than written here. So because dyadic rectangles overlap like crazy, why box condition implies this Carlson-Chang condition is absolutely not clear. It's absolutely unbelievable. It cannot be so, but it is. It is not only in dimension 2, but also in dimension 3. And as I said, in dimension 4, we don't know. Okay, so about Poincare inequality. So let me tell you in what we proved in a different language. So let us consider the graph which corresponds to dyadic rectangles. So the root of this, so graph will be gamma. So the root of this graph is the unit square. Now, what are children of the unit square? You can split the unit square in a vertical middle line, and you will have left and right sons. But you can also split to two dyadic rectangles by horizontal in the middle, and you will have another two sons. You will have up and down son. So it will have like four sons, left, right, up and down. Now, if you will repeat this procedure for sons, you will see that left son and down son have the common son. So the graphs will start to have cycles. So the graph of dyadic intervals is just dyadic tree. The graph of dyadic squares is just a quadratic tree. But the graph of dyadic rectangles is a very complicated graph because it's a rooted directed graph, but with cycles. And none of the cycle is directed. So it's an interesting graph. It's a rooted directed graph without directed cycles. So it's possible that what we are doing can be somehow pushed to many graphs of this type, but because we cannot push it even to dyadic rectangles in dimension 4, so to say about general graphs is a little bit strange. But here is the general theorem. If for the graph you can prove this theorem, this result, down line, this line, the last line. I didn't explain what is I. So what is I? What is this operator? So on the graph, you have just positive function and just some positive numbers assigned to each vertex. And I is the summation. It's like integral. It's summation up. So you take a vertex and go up the graph. If it's a tree, you have only one way to go to the root. If it's a graph with cycles, you have many ways to go to the root. Unfortunately, because there are no directed cycles, you don't go around and around and around. So you finally go to the root. And so this is operator I. So you can call it integration on graph, or you can call it Hardy operator on graph. So, and what we actually did before this minute was this inequality. We described measures such that this holds if graph gamma is the graph of dyadic rectangles. Okay, but there is a general theorem. If you have such a graph, which is directed graph, rooted directed graph without cycles, with cycles, but without directed cycles, it turns out that this inequality here is equivalent to this inequality. And why it is funny? Well, first of all, it's not a difficult result, but it's beautiful because this is Poincare inequality, right? Think that mu is a probability measure. So you have function, you have average of function, and so you are looking at the Poincare inequality. Why you are looking at the Poincare inequality? Because if you think about integral of f as your test function, what is f itself? If integral of f is called g, then f is the derivative of g. So this is exactly Poincare inequality. Here you have derivative, here you have function itself. In my notations, here you have integral, And here you have function itself. Well, anyway, it's a Poincare inequality. It's weighted Poincare inequality, which is often important. And so here we have that as soon as we prove our embedding, and believe me, this is exactly embedding theorem, this last line, we have automatically Poincare. This is an easy direction, but a funny direction that if you have Poincare, then you necessarily have embedding. So these two answers to these two questions are the same. Okay, so here I just formulate the main theorem once again. So we have embedding. You see that's dot. In front of dot there should be 1. Of course, I don't write 1 because it's 1. And so that's the embedding we want. And it holds if and only if we have a box condition, which defies thinking, but because, for example, it looks like contradicting the Carlson, but it doesn't, and it's a true result with a very combinatorial proof. So in particular, this box condition implies open dyadic sets condition, or Carlson chunk, as I called it. And even this is kind of very difficult to believe that it's true. For if measure satisfies 13, then it satisfies 14, but that's true. And we don't have any direct proof. So here I try to draw the picture of dyadic open set. Maybe it's not a very good picture. So it's the union of dyadic rectangles in all directions. You see, it's basically any open set, because you're allowed to unite any number of dyadic rectangles. And then, like in this Carlson chunk, you should consider all red guys, all dyadic rectangles, which are inside this open set. And they should be on the left. And box condition is much simpler. You just consider the box, and then you consider red guys inside. So this picture left and this picture on the right are very different, but it turns out that if you have condition for the right picture, you have condition for the left. Here's some technical things. There's no time for technical things and even for explanation what's going on. But maybe I will explain a little bit, maybe a couple of words about the main tools. Yeah. Well, that's basically some kind of energy estimates. So what is energy of measure? So energy of measure, you should consider all dyadic rectangles. Take measure of every sum. That's the energy of measure. So sum of measures squared of all dyadic rectangles. And if I delete delta here, it will be this energy. And by the way, that's on the right. This energy is on the right. So mu is just the mass of mu, mass of measure. Delta is a small number. And what is E delta? So E delta is like you consider the same sum of squares, but you cut it. And so you throw away many, many rectangles from it. You leave only those rectangles such that if you consider measure of this rectangle, consider its fathers, there can be several, because we have cycles. Consider measure of fathers, consider measure of fathers of fathers, consider measure of fathers of fathers of fathers, and etc. And sum them up, all this, then this sum suddenly becomes less than delta. So you start with some guys such that this huge sum is less than delta. All other guys you just discard. And so it's kind of cutoff energy, and that's the main estimate. That's the main estimate. So for every epsilon, positive epsilon with some constant which depends on epsilon, we always have this estimate of energy, of this cutoff energy, and even better for this special case. On dyadic rectangles in 3 dimensions, we cannot prove. You see, the smaller epsilon, the better for us. For example, if we can prove that epsilon is 0, it would be great. But it's not true. So in rectangles in 2 dimensions, you cannot make epsilon 0. But you can make it almost zeros. It can be any epsilon. It's actually like that. In 3 dimension, we cannot even come to epsilon 0. The best epsilon we can find is 1/2, but it's also enough for the proof. So these are main results, and so I'll try to explain them, but I'm not sure that I have any time. And here I said some words about holomorphic functions. Holomorphic functions. So let's say something about holomorphic functions. So we have these situations like B disk, 3 disk, etc., multi-disk, and we have some Hilbert spaces of analytic functions. This is H2, Hardy space. So these are functions, sorry, it's Z1, Z2, not ZZ. So it's 2 variables, or ZW, so Z here, W here. And sum of squares of coefficients is finite, so it's such Hilbert space. Or Dirichlet space, so these are functions with this condition. So if S1 and S2 is 0, it's a Hardy space. If S1 and S2 is 1, it's Dirichlet space. And you have something in between. So what we call measures, Carlson measures for the Hilbert space of analytic functions, if the identity map from the Hilbert space of analytic functions to L2 with respect to this measure is a bounded map. It just means, for example, for B disk, that for any functions from our Hilbert space of analytic functions, this inequality holds. And we call this inequality embedding. So we start with F and we embed it to L2 mu. Okay. And we know the theorem for Dirichlet space because it corresponds exactly to W equals 1 in the previous situation. And so translating by some soft analysis, beautiful but soft, we got full description of measures for Dirichlet space in B disk. If now your smoothness here S1, S2 is not 1 as in Dirichlet space, but close to 1, then we again can do that, because then W will be certain product, and we can handle that and give necessary and sufficient condition. But somewhere when the smoothnesses go from 1 to 0, somewhere, we have no idea where, the phase transition happens. Something strange happens, because we know that here, when both of S's are equal to 1, we can describe such measures. But if both of S's are 0, so we're in seemingly the simplest case, where in the case of Hardy space in B disk. we don't know the description of Carlson measures. And the reason we don't know the description of Carlson measures for hard disk space and B-disk is very strange. So first of all, we have a natural conjecture that these are exactly the same Chan-Carlson measures mentioned above. And this condition is sufficient because Ellis Chang proved that if you take the function on B torus and extend it B-harmonically to B-disk, then Chan-Carlson condition will be necessary and sufficient. But H2 is small part of this extension. It's B-holomorphic function, and we were talking about B-harmonic function. So for B-harmonic function, we know necessary and sufficient condition. B-holomorphic are inside, so this condition is sufficient. But is it necessary? In one dimension, it was very easy. The necessary and sufficient condition we got from very simple test on the very simple functions, on rational functions with one pole. But Carlson-Chang condition is not like that. It's not a box condition. It's Carlson-Chang condition. It's a complicated. It's about open sets. Like Chang-Pfefferman BMO is not the usual simple BMO thing, but about well, Chang-Carlson Pfefferman-Chang BMO. It's a different thing. It's tough. So we know that Chang-Carlson condition will be sufficient for this embedding, but we don't know whether it's necessary. It's just a conjecture. Well, let me tell you something. So now I will be very kind of flying over you. I don't have time to explain too many things. So let us consider so-called small Hankel operators. Now in B-disk. Now this is not B-disk, this is B half plane, but it's the same as B-disk. So what is the description of the symbols of small Hankel operators? In one dimension, it's Nihari's theorem, and it's BMO. So this function should be from analytic BMO. Symbol from analytic BMO is the same as the bounded operators from H2 in C plus to H2 in C minus. But if you now consider this situation, the conjecture is that answer is that phi is in Chang-Pfefferman BMO. So if we would know that, and if we would know how to extend it to Hankel operators with Hilbert space values, then we would prove this conjecture about Carlson measures for the hard disk space in B-disk. And now experts will tell me, but we know when small Hankel operators are bounded. And yes, you are right, this is exactly Chang-Pfefferman BMO, because it's a famous theorem of Ferguson and Lassie. So it's a theorem from 2004 of Sarah Ferguson and Michael Lassie, which was published in Acta Mathematica. Very beautiful. And approximately a year ago, I found a mistake. So it's now accepted that it's a mistake because they publish a retraction. And so this Nihari theorem for B half plane, or if you wish for B disk, is not known. It is probably true because, I mean, I found mistake not in this claim, but in the proof. And let us assume that it's true, because it's like 95% it's true. And let's assume that we can extend it to Hilbert space valued operators. So then by some simple argument, which is below, but I don't have time to show you, we will have that description of embedding measures for the hard disk space in B-disk is exactly the same as the embedding measures for B-harmonic functions in B-disk. And for those we know the answer, it's Chang-Carlson measures in B-disk. But I'm not saying that Lacey-Ferguson is equivalent to the description of embedding measures. From that description, it would follow the description of embedding measures, because to describe the embedding measures, I don't need all fees. I need only very special fees. But even for those special fees, nothing is proved. Okay, so I guess I should stop here. And thank you very much.
Thank you. Now we have time for questions.
Mm-hmm. Yes.
I probably won't see you, or we won't see you if you raise a hand. So please just go ahead. And
so should I stop sharing? Yes.
No, that's
maybe
fine.
not. Maybe not. It can be useful, right?
Mm-hmm. Yes, exactly. So let me go to the list. I don't see anyone. Oh yeah, I see. I see a hand. Yes, please go ahead. Yeah.
I have a question. Like in the theorem you had for graphs with cycles, if you know the constants for the point k inequality, do we know the other constant?
1 second. Where I should go?
It's the main theorem, I think, on the
main theorem, right? Mm-hmm. Let's go to the main.
like C and C tilde.
Below, right?
Yeah, yeah.
Here somewhere, right? So even where it's formulated,
down, I think.
Where it's formulated as a theorem, it should be formulated somewhere as a theorem.
This one.
Yeah, theorem, right? Mm-hmm.
If
yes.
You know, like the constants for the point k inequality, do we know the constant C tilde?
1 second. Constant for what? I don't understand. If I know the constant for what?
Can you go up in the theorem, like
this way?
Yeah, this one. If you know the, let's say, if you know the constant C. Do we know the constant C tilde, like from the, in terms of C, or like?
You mean how to find C in terms of C naught?
C, yes.
It's a very good question. It's a very non-linear relationship. Yeah, you can calculate it from the proof, but yeah, you can calculate it from the proof, but it's pretty nasty.
Thank you very much.
Right. Other questions? Well, if not, then let's thank our speaker once again. Thank you very much. And we'll see you all next week.
Thank you. Bye.